Thank you. And yeah, so Martin already talked about Capybara, and today I'm doing a short demo of Capybara using a experimental compiler which implements the type system we are currently formalizing. And so what is a capybara? So apparently it is a cute animal, and they are actually in Singapore Zoo. And so if you like capybara too, you could go and see them. So and this picture is shot by Wen Hao. So yeah. And what is system capybara? So it is actually a type system based on Kepler's, which is the system I'm going to present on Thursday on Uppsala. And it's based on capture checking, and it makes use of capture checking or it extends capture checking to reason about separation and freshness. And maybe let's first look at what is a capturing type. So it's a really, really quick introduction that capturing types, the core idea of capture checking is to track captured variables in types. And to do that, we augment types with the capture set, as you see here, which is like the capability a value can capture of this type. So we can look at some examples actually. Yeah, so now we have, this is like in that small experimental language, and now we are using this scoped capability pattern, which Martin showed just now also, which we say, now I have console capability locally, and I can use it to print things to console. And now if you have a function that uses that capability, what we will get, you will return, okay. Yeah, you will, let's look at what type it has. So it has this type, which says this grid is a function from unit to unit, and it's capturing console, the capability. And it's like basically saying that I'm a function that will perform console I/O. So that's the key idea of capture checking. And if we ever try to pretend this to be pure, of course we get an error. Okay, should be like this. Yeah, so we say we are pretending it to be pure, so this is like a pure arrow, and we are asserting it is capturing nothing, and we are actually using some effects, and of course the compiler will not be happy about that. And now maybe let's have some general idea of separation and freshness. So it's basically a aliasing controlling problem. So for instance, like if we want to run OP1 and OP2 in parallel, and we want to ensure data race freedom, and what matters is what OP1 and OP2 accesses, or like what aliases are OP1 or OP2, or what references OP1 and OP2 is referencing. And if they are both reading from some mutable state A, it's fine. But if that's another case, like if someone's reading and the other is writing, or both are writing, then no, it's a data race problem. And to detect this, what matters is what OP1 and OP2 accesses. And similarly, if we want to have the resource pattern that, let's say F is a file, and we first close it, and then we are running some operation that access that file, then it should also be a problem, because then we are basically accessing a closed file. So all these patterns, capturing types can help because we are essentially reading about the captured variables of these closures and operations and values. So if like here, OP1 or OP2, if it access A, or if there's some OP access F, then it will somehow be present in the capture set in the type of these values. So then we can make use of this information in the type system to prevent these bad accesses, to reason about these separation and freshness properties statically. So Now let's see. So Capybara is based on this general idea. So we are in capture checking, and we have some aliasing information. We have some reference information, and now we make use of this information in the type system to reason about separation and freshness. And how do we do that? So the first step of Capybara is to qualifying capabilities with access modes. Which you will see here. So basically, we are adding another M, which will not be present in the surface language of Scala, of course, because we do some inference. But in theory, we have this access mode on capturing types. So it can either be maybe read-only, or like it is owned, or something like that. And we can again see this in action. That yeah. So here we are defining some mutable capability. You can understand it as like a mutable capability, which is a reference that's holding a mutable data of I32. And here you can say I only want the read-only mode of a reference, and I'm just reading from it. And if like here, if we have an F that reads from capability A, then it will be, of course, only capturing read-only A. So apart from qualifying the types with access modes, we can also qualify the capabilities, which represents how the capability references, which represents how these capabilities are used with these modes. And now we know that F is only reading from A. And if now we do par, which is some hypothetical library function, which runs two functions in parallel, you will see that it will pass, of course, because both are only reading from A. And if here, if we only have a read-only reference of X in this read function, and if we ever try to write to it, of course, our system will not be happy because we are expecting a mutable reference, but we got a read-only one. So, the general idea of this is that in the type, the access mode in the type represents the permissions, the authorities you get from this type, and the access mode on the capability references means like the price you have to pay for running this operation. So it's like F will pay the price of read from A, and to do that, and to yeah. So. And if you have another function that is just writing from writing to a reference, and maybe let's comment this out for better readability, and okay. And you will get another capture set of this function, which is like G, which is capturing A, and it says that G is actually writing. It can write to A. So it has to also pay the price of writing to A, so it cannot possibly be run in parallel with G itself or F. Both will be an error. Like here, we get a separation error because G and G, they are both writing to A, which is apparently shouldn't be allowed. So yeah, and this is the first step of this idea of using capture checking to reason about separation, and then with this read modes, we already see that we can reason about we can prevent some sort of data race freedom, and now I can show you more examples of reading about separation reasoning in this calculus. Sep check, okay, yeah. So let's say again, if you saw Dimi's talk yesterday, we have this swap example, which we want A and B to be separated, and like if here you have two references A and B, and as Martin mentioned, just now we have some fresh roots of capabilities. So this means that we are replacing cap with existential captures, and this is an example of this. That we say, if you create a new reference, then you are getting a new, fresh capability, which is separate from the rest of the world, and that's why here swap A and B is allowed. So you can do that because A and B, they are separated. But if you do a swap A and A, it will of course be an error. And if you put A into an alias, like T1 is an alias of A, and you swap A with T1, would that work? Of course not, because we see that our system can make use of the capturing information to know that T1 is actually a reference of A, like we see here, like the type of T1 is the ref of A. So we know that T1 is just an alias. And now the next step is freshness. 5 minutes, okay, yeah, freshness. So let's see that. So yeah, I have some example of some example API. So it's not doing anything. It's just to show our type system. We have an open file, which is opening a file for us, open a new file handle for us. And we can read from it, we can write to it, and we can close it, of course. So if we do this, read file f, it will work, of course, and it will work. And if now we close it, close f, which we see here, we have consume, which in our system means that we are like dropping this capability and preventing it from being further used. And we write file or read file again, it will be a consume error. And similarly, if you have an OP that reads the file, and if you want to call this OP after you have closed this file, then it will similarly be a consume error because with capture checking, these aliases are all in the type system. We can reason about them.
You're saying line 12 is the string hat in the result intentional?
Yes, it is intentional, because in string in this demo language is represented as array, and the array is tracked. So okay, yeah. Actually, I have another thing. So actually, with consume, we can model affine functions too. Here, if we have this run once, which says it is consume itself, then it can only be run once, of course. And if you try to run it twice, it will be an error. So with consume, we can actually model this affine thingy. And finally, so we have the formal system, which has informed and inspired the development of this demo compiler, and also the separation checking implementation in Scala'3. And it is based on Kepler's, and I'm going to present it on Thursday in the morning. And thank Martin for talking about the essence of this work. I think it already covers what I want to say. And please come if you are interested. And in the end, thank you very much for this, for being here and listening. So now we are developing the system, and it reasons about separation and freshness, and the current developments are like the formal calculus that is formalizing these ideas. And we hope to establish some connection to separation logic. Therefore, we want to do some semantic type soundness. And maybe we can encode Rust in Capybara because we can reason about these things, and maybe we can have a type system for Rust that is much better than Oxide or or featherweight Rust. And and we have a prototyping implementation of the core type system. So, and also an experimental separation checker in Scala'3. So if you are interested, you can scan this QR code, which will bring you to a project page of Capybara. And we also have a project page for capture checking in general, which is just couplers.cc. So if you are interested, you can check them out. And just have time. Okay, yeah, because we still have time, I can show a final example, which is the array buffer thing that Martin has mentioned, but it's done a bit differently. So I have this string buffer, and this code is actually working, so it's actually implemented, and we have some APIs for this buffer, which we say we can append to it, and we can get the result of it. So appending to it will not consume it. It's like modifying the string buffer. And if you retrieve the result of it, and like it's the string you are building, then it's like you are finalizing this string builder, and you should not use it any further. And now we can actually do that. So like if we compile this code, and if we run it, it will show hello world, which is what we've done here. And if we want to append the string after we have got the result, after we have finalized the string buffer, of course, we will get an error. And similarly, we can't bypass the system via some aliasing. So it will always be detected. And yeah, I think that's all. And thank you all for listening.
Thank you very much, Yichen. We have time for one quick question, maybe?
How do you handle functions which kind of alias themselves? So a function which, say, takes a ref that you defined and returns a reference?
A function that references itself?
No, so like you had that example with ref, right? That had an integer inside of it.
You mean like...
I guess the second one.
The second one.
So if, say, you had a function which took a ref and returned a ref, like as an argument, and then returned it as a result.
Yeah, so it will... So if you write it like that, it will be failing because it's essentially like hiding the aliasing. Like exactly. you are forgetting the aliasing. Okay. Yes. Oops. Let me comment this out. Yeah. So now it will say that we are treating this capability X as fresh, which is the case here, but it's not actually fresh. And to make it work, you must consume it, because that will make it actually fresh. Like it will prevent X from being further used. And okay, yeah, it works. It will prevent X from being further used, and it can be treated as fresh. And internally, or like in the theory, we have this thing. So this returned fresh thing is modeled with a existential. And we say to actually introduce an existential, you have to ensure that the witness is fresh. And to do that, you either consume it or you actually is creating some fresh things.
Or if you don't want to consume, you just have to be explicit.
You be explicit. That will also work. Yeah, because then it's not existential, it's a normal capturing type, and it's just preserving the alias.
And I guess a quick follow-up, do you support then also if I have references inside of some other structure? So if I had this ref in a tuple, let's say I took a tuple of two refs.
Yeah, we can do that, like a ref pair, maybe just P, because A ref hat, B ref hat, and we can say we want to make P. So we can do it like this.
Maybe the same signature that you had before, where it takes a P and returns one of the references from the P.
Yeah, okay. We can do this too.
let's say I return the first tuple of the first element, so like a ref. Yeah.
Yeah. Ref p dot a.
Okay.
We press for time. Maybe we can make this demo of over the lunch or
It's not working. Okay, but I think this will work. Sorry, this is a bit buggy, but
Yeah, it's okay. I mean, I just wanted to see how
this
it looks
works.
and if it works. Yeah.
And
Thanks.
if you okay.
okay. Thank you very much, Yichen.